Okay, it's my great pleasure today to be able to introduce Andrew Dessler from Texas A&M. And, by way of introduction, to give you a sense of how distinguished our visitor is, he actually has a website, andrewdessler.com, where he has a bio, which presumably comes in handy quite regularly because it's beautifully written, and so I'm just going to read this bio that's on his webpage. Andrew Dessler is a climate scientist who studies both the science and politics of climate change. His scientific research revolves around climate feedbacks, in particular how water vapor and clouds act to amplify warming from the carbon dioxide that humans emit. So he has an interesting background. During the last year of the Clinton administration, he served as a senior policy analyst in the White House Office of Science and Technology Policy. Based on his research and policy experience, he has authored 2 books on climate change, The Science and Politics of Global Climate Change, A Guide to the Debate, and I highly recommend that. I read some of that book, and it's really, really interesting about how climate scientists do climate scientists and why they believe what they do. There's some really good lessons for us. And Introduction to Modern Climate Change. This latter book was the 2014 American Meteorological Society Louis J. Batten Authors Award. In 2012, he received the AGU's Ascent Award from the Atmospheric Sciences section to reward exceptional achievement by a mid-career scientist. And in 2017, he was named a Fellow of the American Association for the Advancement of Science. In recognition of his work on outreach, in 2011, he was named a Google Science Communication Fellow. Prior to his work on climate, his research focused on stratospheric photochemistry, and he has a book there too, The Chemistry and Physics of Stratospheric Ozone, which I guess you said is in its 3rd edition?
No, that's only one edition.
That's only one edition, okay. It's the other one. He's currently at Texas A&M. He has a background degree in physics and chemistry from Harvard, physics from Rice, and he did postdoctoral work at Goddard Space Flight Center. And before that, before entering graduate school, he actually worked on Wall Street in the energy group and the first Boston corporation doing mergers and acquisitions analysis. So a very varied background. And I know him partly too through his Twitter feed, where he has many obnoxious posts that are largely directed at pointing out the idiocy of climate change deniers. So he serves an important societal role in that regard as well. So thank you, Andrew.
Thank you, Tim. So I'm going to talk today about something that I've been working on for, in one way or another, for a very long time, trying to estimate climate sensitivity. Okay, so for people that don't know that, I'm going to start off by giving you a little background, and then we'll talk about climate sensitivity, and we'll go over some different calculations. Before I begin, though, let me acknowledge my co-authors on the work I've done here, Torsten Jurtsen, Bjorn Stevens, and Piers Forster. They've co-authored the various papers that have gone into this. And so we'll start off with a little energy balance 101, all right? All right, so imagine you have a planet, and the planet is the temperature's not changing, so the atmospheric composition is constant. And consistent with that is the TOA flux is basically 0. And these two things have to go together. If the flux is 0, the climate's not going to be changing. And now, let's imagine we do an experiment. We quadruple carbon dioxide instantaneously. All right? So what that does is it generates a giant TOA flux. TOA is top of atmosphere flux and balance. You add a lot of carbon dioxide to the atmosphere, you throw the planet out of balance. The temperature, though, doesn't instantaneously change because it has finite heat capacity, so it can't change instantly. So the instant after you quadruple carbon dioxide, the climate hasn't changed. Oh, and I should say, we call this the radiative forcing. People talk about forcing. All they're referring to is an imposed energy imbalance on the climate system. So you impose an energy imbalance, you generate an energy imbalance, and so what's going to happen? What's going to happen is the climate's going to change. It's first law of thermodynamics. Okay, so what happens is you start seeing the climate starts warming. It warms really rapidly at first, and then after a few decades, it kind of turns over and warms a little more slowly. Now, at the same time the climate is warming, we also know sigma t to the 4th. Warmer things radiate more, and as the planet warms up, it pushes back on the imposed energy imbalance. And so here's the same plot I showed you. Here's the climate, it's warming up. And here's what the TOA flux looks like. It's 0, and all of a sudden we quadruple carbon dioxide, and then as the climate warms, the system tries to head back to equilibrium. So this is what climate does, okay? You perturb the energy imbalance, and then the temperature adjusts. Now, eventually what happens is if you run it out long enough, and I still don't know if they've actually run this out long enough, but what ends up happening is you end up essentially leveling off. It's probably still warming up a little bit, even after 4,500 years. But the TOA flux goes back down to 0, but the climate's a lot warmer. So you add some carbon dioxide to the atmosphere, you generate an energy imbalance, the climate warms up. As it warms up, it wipes out that energy imbalance. Eventually, the system reestablishes equilibrium at a warmer temperature. So if you ask the question, why do we have the climate we have? The answer is because that's the climate that balances energy. So the reason we have an average temperature of 14.5 degrees Celsius or whatever it is, because that's the temperature that balances energy for the planet. And if the energy balance is perturbed, which is what we're doing by adding carbon dioxide to the atmosphere, the temperature of the planet will change until it reestablishes energy balance. So in a nutshell, that's climate science. Now, the interesting thing is, if you take these two quantities, this one right here, temperature and TOA flux, and you regress them against each other, this is what the plot looks like. And you get something which looks kind of like a straight line. And from this, we've generated in fact, you can fit a straight line to it. After all, you can fit a straight line to anything. But you generate the dominant, what we call the linearized energy balance equation. And it basically says that the TOA flux is equal to the forcing plus lambda times temperature. And you can kind of see that here. Whoops. Go back. You can see that right here. So the intercept is the forcing. So that's right here. That's, you think about that, that's the amount of radiative forcing. This slope is lambda. And then the x-axis is temperature, and the y-axis is TOA flux. And so people use this equation. We'll talk about how you use this equation to estimate climate sensitivity. All right, so let's talk a little bit about this. Okay, so lambda is really the key parameter in understanding climate sensitivity. So it's how much change in TOA flux there is, how much change in net flux there is per degree of warming of surface temperature. So if you warm the surface 1 degree, how much does that change top of atmosphere flux? So that's what lambda is, and that essentially is climate sensitivity. Put another way, alternatively, minus 1 over lambda is how much warming is required to offset a 1 watt per square meter forcing. So if I perturb the energy imbalance by 1 watt per square meter, minus 1 over lambda is how much warming is required. Now, the reason there's a minus sign, this confuses graduate students everywhere, is because lambda, when you write the equation this way, has to be a negative number. Yeah. And the reason is that forcing is a positive number. And for these two terms to oppose each other, which they have to do, temperature in response to a positive forcing is going to be positive, lambda has to be negative. So by sign convention, lambda is a negative number. That's why you're going to see this negative sign appearing. Just, if it confuses you, ignore it. Don't, it's not, for this analysis, it's not important. But all you have to know is 1 over lambda is how much warming you get, is how much warming you need to cancel out a 1 watt per square meter warming. And similarly, if I give you a warming of F, then the warming in response is minus F over lambda. All right, so this leads us to climate sensitivity. All right, so climate sensitivity is conventionally defined as the amount of warming you get in response to doubled carbon dioxide. So that's the conventional definition. So we can write climate sensitivity as the forcing from doubled carbon dioxide, which is about 4 watts, a little south of 4 watts per square meter, divided by lambda. And again, there's that irritating negative sign in front of it. And that gives you a positive climate sensitivity. So again, it's the equilibrium warming from doubled carbon dioxide. And this is, people will say, this is the most important number in climate change. Because what it tells you is, if you emit some carbon dioxide, how much warming you're going to get. And there's a big difference between a climate sensitivity of 5 degrees for double carbon dioxide and a climate sensitivity of 1 degree for double carbon dioxide. One would be really, 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 really bad. The other would just be bad. So it is crucial that we nail down this number. So I'm going to go over first is some of the history of the calculations, and then we'll talk about where you can fall into a trap in this calculation. And then I'll sort of summarize with my own calculation based on sort of a new approach. All right, so let's go with the simplest calculation we can do. Let's imagine the Earth is a black body. All right, so we know for black body radiation, sigma t to the fourth. Okay, everybody knows that. Now, remember, lambda is a change in TOA flux per degree. So we can just take the derivative of this. And we know that's 4 times sigma t cubed. And we also know the Earth radiates at about 255 Kelvin. That's the irradiation temperature. It's about 5 kilometers up in the altitude, or about 500 millibars. So for a black body radiating at 255 Kelvin, lambda is minus 3.8 watts per meter squared per degree Kelvin. So if you warm a black body by 1 degree Kelvin, it will radiate 3.8 watts per square meter additional radiation. Okay, so let's calculate climate sensitivity now. All right, so remember, climate sensitivity is F over lambda. All right, so F is about 4 watts per square meter. That's the forcing for doubled carbon dioxide. And we know that pretty well. That's just a radiative transfer calculation. Lambda, I just calculated, is minus 3.8 watts per square meter. And again, those minus signs cancel. So you end up with about 1 degree of warming. So this is your 0th order calculation, back of the envelope calculation. You get about 1 degree of warming for doubled carbon dioxide. Now, I'm going to show this plot. This is a summary plot. I'm going to show a bunch of different versions of this. I should give credit to Steve Schwartz, who published an earlier version. He actually sent me, this is an updated version from the one that was in this paper that I really like. And we're going to sort of go over time the various estimates. But this is the first estimate we have. And Steve labels it Stefan Boltzmann. Neither Stefan nor Boltzmann actually did the calculation, but it relies on sigma t to the fourth. So we can put that here using sort of late 19th century physics. You get about 1 degree for doubled carbon dioxide. All right, so this is the first calculation. Now, this is wrong. And it's wrong because things change when the climate warms. So what are the kinds of things that change? Well, water vapor increases. And water vapor is itself a greenhouse gas. So that increases the emissivity of the atmosphere. That gives you even more warming. In addition, ice melts. Okay, so you warm the climate, you melt ice, that changes the albedo of the Earth. So that increases the albedo, decreases the albedo, so you get more solar absorbed. That gives you more warming. In addition, this is maybe more speculative, low clouds. Most of the models predict low clouds occupy a smaller fraction. That gives you a positive cloud feedback. So when you take those into account, the first person to do a calculation that actually took those into account was Arrhenius. And they used to call CO2 carbonic acid, which sounds better, I think. It sounds more evil, which it should. So Arrhenius did this calculation in 1896, and he came up with a value of about 5, between 5 and 6, which is really an astonishingly, amazingly good value, considering how little they knew about the planet. They didn't know what fraction of the planet was covered by clouds. They didn't have any measurements of, virtually no measurements of the atmosphere. And so he came up with this prediction, and he really said, if we're burning coal, if we keep doing this, we're going to warm the climate. And in some sense, he figured everything out. You know, all we've done in the 120 years since then is kind of reduce the uncertainty and stuff he figured out. Yeah.
How did you treat the feedback?
You know, he had them in there. Let me just go over this. These are things he got right, because I'll get to that in a second. So he understood temperature was determined by energy balance. He understood the balance at TOA is a fundamental constraint. Actually, for 50 years after that, people were still arguing whether it was a surface energy balance or the top of atmosphere energy balance. And he understood it was the TOA flux. He understood the IR opacity was due to water vapor and CO2, and he knew water vapor was a feedback. So he knew that was a feedback. And I mean, again, he had to use some assumptions, and I would have to look at the paper to remember exactly what assumptions he made. It's been a long time since I've read the paper. But he actually knew it was a feedback. He also knew that CO2 was logarithmic. The relationship between CO2 abundance and forcing is logarithmic. And he understood the greenhouse effect works by radiating at a colder temperature. I won't talk about that. But I mean, he got almost everything right. It was really a tour de force of science. And I would encourage anybody who wants to know more about this. Ray Pierre Humbert gave the 2012 Tyndall lecture at the AGU, and he goes over the history of climate science. He spends a lot of time talking about Arrhenius. So I encourage people to watch that if they want to know more about Arrhenius. So the next estimate of climate sensitivity is the Charney Report. So 1979, this I consider to be the first modern assessment, even though they really didn't have very much to work with. They had 2 model runs. They had a GFDL model, I think a GISS model, and they just had a physical intuition. They were a bunch of smart people sitting around in a room, and they came up with this idea that we estimate the most probable global warming for doubling of carbon dioxide to be near 3 degrees with a probable error of plus or minus 1.5 degrees. So they came up with this range of 1.5 to 4.5 Kelvin. And so we go back to our diagram. This is the Charney Report. And this is really, again, this is sort of the first modern assessment where these people were using computers. They had some data, but really it was still very impressive. A very impressive effort here. And so now we get to the IPCC period. So the first IPCC report is 1990. Second report was 2001. Third report is, 1990, 1995, 2001. First, second, third IPCC reports. And you can see they essentially copied the range. And so my theory is that there were 2 things going on. 2 things going on here that explain why the error bars aren't going down, because we were learning a lot about the climate system. And in fact, people still kind of criticize climate science. You've been working on this for 40 years and spent billions of dollars. Why can't you get the climate sensitivity error bars down? And what's happening here, in my opinion, is we are learning a lot about the climate system. And what we're learning is that the error bars should have been a lot bigger back here. They really didn't. They were guessing at what the error bars were, but because they were unknowns, they really weren't putting the error bars as big. And so what's happening is there's this cancellation between the error bars getting smaller, but our understanding of the uncertainty is getting larger. And so that's led over this period, because in 2001 we knew a lot more than we did in 1979, but the error bars are basically the same. So then you get to 2007. So this is the 4th IPCC report. I think they were sensitive to all of the criticism of not reducing the error bars. So they popped up the bottom error bar up 0.5 degree to 2 degrees. I actually don't know. I wasn't in the room, but I can't believe that was in effect. And they also came up with the most likely estimate of 3 degrees for doubled carbon dioxide. Now then, something kind of weird happened. Or not weird, but science is always advancing. And there was this new set of estimates of climate sensitivity came out. So let me just take a step back and say, how do you estimate, where do these numbers come from? Well, the numbers come from models. Obviously, you can run a model, you can double carbon dioxide, and that gives you a range of 2 to 4.5, give or take. And those are the older models. The new models, actually I won't even go into that. Ask me about the CMIP6 models if you're curious. So you can run climate models, but you can also look at observations. And so, for example, you can look at the response to volcanic eruptions, or you can look at last millennium, or you can look at last glacial maximum. You can look at the Eocene. And these all give you essentially a pretty consistent 2 to 4, maybe 2 to 4.5 range. But then there's one more set of data that started coming along that gave a slightly different answer. And it was the instrumental period, the period from 1850 or the late 19th century to today. And if you look at these, you see all of these values at pretty low climate sensitivities. And so I was not in the room, but what I'm guessing happened is these people looked at this. They said, look at all this ink that's down here. We can't put the bottom end at 2 degrees because there's all of this ink that's over here below 2 degrees. So so what they did is they actually reduced. So I'll show you the plot in a second. I thought it was the next slide, but it's not. They actually reduced the error bars. But before I get to that, let me talk a little bit about how these measurements come about. Okay, so how do they get these instruments of instrumental period? Okay, so we start with our favorite equation, linearized energy balance equation. So over the 20th century, we have pretty good measurements of surface temperature. So you can get the GIS, NCDC, HAD crew. We know what the surface temperature is, I think reasonably well. Forcing we can't measure, so we have to get forcing from a climate model, but there's really no way around that. And then top of atmosphere flux, you can get from some combination of assumptions of what the 19th century was, along with ocean heat content data, so Argo data. So we have estimates of these things, and so you can solve for this, and you come up with an estimate. And then once you know this, you can come up with climate sensitivity because you know what forcing from double carbon dioxide is. So this is how you get lambda from the 20th century record. And again, if you look, there's all of this ink down here below 2 degrees. And so the IPCC revised its climate sensitivity. It was actually reasonably big news. I mean, I'm someone who pays a lot of attention to it, so obviously it's big news to me. But I think it was big news to a lot of people. The IPCC changed its climate sensitivity estimate. And what they did was they moved the bottom end of the range back down to 1.5 degrees. So I mean, it's really these are pretty small changes, all things considered, but it was reasonably big deal at the time. And it really caused me to start thinking about how do we test this idea. And in particular, I was always skeptical. There was something that just seemed off. You know, as scientists, you have intuition. You kind of look at a calculation, you say, I don't know what's wrong with it, but something seems wrong. And you know, usually you just kind of ignore it and you go on. But I kind of stuck on it because this was a big deal. This was torquing the IPCC's estimate of climate sensitivity. So I was actually on sabbatical at MPI in fall of 2016, and I was working with Bjorn Stevens and Torsten Mjortsen, and they told me that they had this 100-member ensemble. So they took their state-of-the-art MPI Earth system model, so it's a full-blown coupled model, and they ran it 100 times. So it's really an amazing computational endeavor to run their full model 100 times for 155 years. So it's 15,000 years of model time. The only difference between the runs is the initial conditions. Identical physics, identical historical forcing. So the only difference, again, is the initial conditions. If you want to know more about sort of the work I'll talk about in the next couple of slides, it's in this ACP paper. It came out about a year ago. And so what we can do is, and here's a picture of what the ensemble looks like. The white line is GIS, and the colored line is the different ensemble members. So it kind of looks like what you expect. It basically follows the model. There's a lot of noise because internal variability in the models is not going to be the same as it is in the atmosphere. Okay, so what are we going to do with this? Well, this is a really interesting experiment because what we can do is for each ensemble member, we can calculate lambda. And so we know the temperature, we know the forcing, we know the top of atmosphere flux. It's a model. We can get all of that out. So if we can calculate lambda for each ensemble member, then we can calculate climate sensitivity. And we know what the climate sensitivity is of the model because we can double carbon dioxide and run it to equilibrium. So this is a test of does this method work? And so we did this. We calculated lambda for every one of the 100 ensemble members, and this is what it looks like. And the answer is the method doesn't really work. It doesn't give you a single value. And the model's actual true value is this is the average. I can't remember if this is the average of the PDF or the true value. It's pretty close to this. I thought the true value, I think the average is 1.43, and this is the actual true value, about 1.37 or something. It's pretty close. On average, the ensemble average is a good estimate, but any individual ensemble member may not be a good estimate of the lambda, of the climate sensitivity. And realize this is purely due to initial conditions of the model. This is an initial condition problem. If you change the state of the ocean and the atmosphere in 1850 and then you run the model, you get different answers. And what this basically says is, if you only had one ensemble member, and I gave it to you, and I said, what's the climate sensitivity? You could get very different and very wrong answers. And so just to give you an idea of what this looks like from ECS, so this is lambda, we'll convert this to ECS by doing F over lambda. You get something from 2 to almost 4 degrees. And so this is really troubling because the thing you have to realize is our historical record is one ensemble member of some theoretical ensembles of Earths. If we had 1,000 Earths and we could run the 19th and 20th centuries 1,000 times, we could come up with this. And we could say, okay, we know what the right value is. But we don't have that. All we have is one value. The question is it down here? Is it up here? What's the true value given what we have actually calculated? Now let me digress a bit and talk about what's causing this. Because you might be saying, why does this not work? All right. So the short answer is that you can think of lambda, which is what you're trying to measure here, as the sum of a bunch of different processes, different feedbacks. So you have the Planck response. I'm not going to go into how these are all defined, but you can think of them as different feedbacks. So I'll just go over one of them, this water vapor feedback, which I've labeled as delta RH for reasons that I won't go into here. So the water vapor feedback essentially means that as you warm the climate, you get more water in the atmosphere. So you add some carbon dioxide, you increase the temperature of the climate system, that increases atmospheric water vapor. Water vapor is itself a greenhouse gas. That gives you additional warming. So that's a feedback. And that process is represented, that process is represented in this term right here. You can think of lambda as the sum of all of these processes. This albedo is the ice albedo feedback. You melt some ice, you absorb more solar radiation, that gives you more warming, that melts more ice. And so we can look at all these individual processes and say which one of these is responsible. And it turns out that it's these two processes, the albedo feedback and the shortwave cloud feedback, that are giving us the spread in lambda. It's almost entirely in the short wave. All right, so let's think about what's causing this here. I mean, what's driving it? So let's think about albedo first. So you can think about albedo feedback as the change in TOA flux just due to the change in albedo per unit temperature. So you warm the temperature up a little bit, you melt some ice, that's going to cause top of atmosphere flux to increase a little bit. So this is this is how much TOA flux increases just because the albedo increases per degree of warming. Okay? So let's look at two ensemble members. Ensemble member 46 and ensemble member 32. Their temperatures look quite similar. They have almost exactly the same amount of warming. But look at their change in ice. This is the global sea ice coverage. They have completely different responses to ice. But everything else is the same. The forcing is the same, the temperature is the same. What's different is the ocean circulation. So the ocean circulation between these two members is different. And that's just because the initial conditions of the two members are different. And if you calculate the albedo feedback, you'd actually see this blue one, ensemble number 46, is going to have a much bigger change in TOA flux because the decrease in ice is a lot bigger. And they have the same delta T, as you can see on this one. So they're going to give you very different albedo feedbacks. And if we look at a histogram of the entire ensemble, you can see a very wide range of albedo feedbacks. And again, this is all due to the initial condition, the state of the ocean when you started out. I will skip through this. And I'll just stay here. And if you want to know the question, what's driving the change in sea ice, it looks like it's these different modes, AMO and SAMO. So the Southern Atlantic multi-decadal oscillation, the Atlantic multi-decadal oscillation, they correlate to some extent with the change in the albedo feedbacks. So again, it's the ocean circulation, basically, that's giving you this spread in lambda. So what's the upshot of this? Okay, so the upshot of this is internal variability confounds estimates of climate sensitivity from the historical record. All right, so you can estimate ECS from the 20th century, but you have no idea if what you get is right because you only have one ensemble member. So there are suggestions, and I haven't covered this, and this is not in any of my papers, that the climate trajectory that we have experienced give us a low bias estimate of ECS. So there's a paper by Tim Andrews and Kate Marvel. And this does not even begin to address large uncertainties in other things like forcing, which we don't have any estimates for. So I started thinking about this, and this led me to sort of the next step on the way, which is, can we do better? So I think there are real limitations. We've gotten the 20th century record as far as we can take it for getting climate sensitivity. We want to do a better job. We want to do better. So let's think about interannual variability. So interannual variability is something like this. So this is 2000 to 2010, and you can see there's really no trend. And I kind of picked this because there was no obvious trend. This is the hiatus period. But you can see there's still big changes in temperature. And those changes are due to El Nino events, basically, modes of internal variability. So it's not global warming, but there are big changes in temperature that are associated with other modes of variability. So I started thinking, can you extract climate sensitivity from these estimates from these temperature changes? And so I said, okay, well, let's see what we can do. And let me just say, this is all from a paper I wrote that came out I don't know, 4 or 5 months ago. Me and Piers Forster. And there are a bunch of advantages to looking at interannual variability. So number one, we have really good observations in the last 20 years. We have ocean heat content, we have satellites flying, we've got almost global coverage of every quantity that you want to know. And in addition, it turns out that forcing changes don't really matter. So forcing is one of the biggest uncertainties in the 20th century record. But forcing hasn't changed that much over the last 20 years. And the forcing changes are uncorrelated with temperature, because the temperature changes are not forced. Temperature changes are internal variability, so they're not correlated with forcing. So forcing adds some kind of noise, as I'll show in a second, but it doesn't really confound. If your forcing is wrong, it doesn't mean your estimate is wrong. All right, so how do we do this? Okay, so let's go back to our favorite equation. Let's think about how we can estimate what lambda is. All right, so the first thing is, we have observations, we have excellent observations over the last 2 decades of surface temperature. We can use forcing, we use updated AR5 forcing, but again, this doesn't really matter. If you get the wrong answer here, it doesn't affect your answer that much. And we have good observations of TOA flux. We're getting that from satellites, from Ceres. And the analysis is to cover 2000 to 2017, essentially the Ceres period flying on Terra. So starting with Terra, Ceres period. All right, so while we do this, okay, so what we can do is we can do a little algebraic rearrangement. We can have r minus f equals lambda t. And so we're going to have we're going to plot up the data, r minus f on the y-axis, temperature on the x-axis, and lambda will be the slope. And if you actually look at what the data says, that's what it looks like. Now, so it's not very good. In fact, you might even say it looks awful. But of course, you can put a straight line through it, because you can put a straight line through anything. And you see that when you do the error bars, the uncertainty is actually bigger than the quantity. I mean, you can't rule out a slope of 0 or even a positive slope, which is physically not physically reasonable, because a positive slope would mean your climate would run away. As you heat up, you're not radiating more energy to space. In fact, you're trapping more energy. That would give you a runaway. So that can't be right. So this isn't very good, but nonetheless, we can work with this. All right. And I'll show you a better approach in a second. But let's work our way through it. Start off with this really not very good approach. All right, so this is an estimate of lambda. All right, so this is an estimate of lambda, but there's a problem with this. So this minus 0.51 plus or minus 0.56 is an estimate. The problem with it is this is a response to internal variability. All right, it's not a response to doubled carbon dioxide, to force climate change, because that's what we really want. This lambda is really the lambda in response to doubled carbon dioxide. And we really have no idea if these are the same thing. Nobody's really worked on this. So this is sort of, nobody really knows. So what we can do is we can account for that. We can account for this. And so what we're going to do is we're going to do the following thing. So we're going to imagine, or we're going to assume that lambda for doubled carbon dioxide, this is what we want, is equal to the observed lambda we get from Ceres, which is lambda to interannual variability. And again, we get this is measured. And then what we're going to do is we're going to multiply this by an adjustment factor, which we get from CMIP5 models. And it's essentially the ratio in the model world of lambda to doubled carbon dioxide divided by lambda interannual variability. You kind of see this cancels that, and you end up with lambda CO2 estimated here. Now, if we do that, then we can estimate ECS as F over, this is the forcing, this is the observed from Ceres lambda, and this is the adjustment factor we get from climate models. Now, there's a problem here. a minor problem, which is there are not doubled CO2 runs in the CMIP-5 archive. So we're going to boldly assume that doubled carbon dioxide lambda is the same as 4 times CO2 lambda, because all the models ran 4 times CO2 runs. You can ask me about that. I think that's a reasonably good assumption. Ask me about it if you're interested. So now we have a way to calculate ECS. We can now calculate using this equation. So what are the terms? Okay, so forcing, we know what forcing is. This is a PDF of forcing from PDR MIP, one of these modeling comparison programs. It's 3.7 watts per square meter, plus or minus, I can't remember, 13% or something. And so we have a PDF for that. We have our measurements from series. So this is what the plot I showed you before. We're going to convert this though into a PDF. So we have a PDF of values of this right here, and we have the CMIP-5 archive. This is what the PDF of this term right here looks like. And again, this is the number of models, and this is the ratio. So the ratio is a little bit less than 1, slightly less than 1, but there's a reasonable range. So now what we can do is we can Monte Carlo this. We can go through and we can pull random samples from each one of these. I didn't do any Bayesian stuff. People always say, oh, you should have a prior and update it. I've talked to people, you get the same answer if you do that than if you just do what I did, which is the poor man's Bayesian. So we just randomly pull samples from these distributions, and then we create a distribution of climate sensitivity. And so what you end up getting is this. This is what the climate sensitivity is. And so this is climate sensitivity on the x-axis. This is the fraction per degree Kelvin on this axis. And you can see it kind of looks reasonable. You get this broad maximum between, say, 2 and 3 degrees. This is the mode. Most likely value is 2.4 degrees. The median is 3.3. And the 17th to 83rd percentile is what the IPCC calls their likely range. All of the values I've given you of 1.5 to 4.4 are all IPCC likely ranges. And this gives you 2 to 5.7 Kelvin. So first off, this doesn't provide any evidence that the climate sensitivity is very low. So that's an important point. All of those 20th century observations were suggesting climate sensitivity was below 2 degrees. We don't see any evidence for that. On the other hand, this is intrinsically disappointing because it doesn't really constrain the upper end. You come up here to 6 or 7 degrees, and there's a non-zero value that that would be a disaster. So we don't like that. We would like to be able to constrain the upper end. I will talk about this. See the paper if you're interested. I'm not 100% sure. I won't even talk about it. Ask me if you're interested in that. All right, so we want to do something better. Okay, so what can we do that's better? Well, the main problem with this, the reason it's so wide, is because of how terrible the correlation between R minus F and temperature was. Remember, that's just a cloud of points. We put a line through it, but it's really not a very good fit. So is there a better way to describe energy balance for the planet? So in my ACP paper from last year, we came up with this alternate, this revised framework. So R, TOA flux, F forcing, those are the same, but instead of describing it in terms of surface temperature, we're going to describe it in terms of atmospheric temperature. And that has some advantages, as I'll show you in a second. So we're going to use 500 millibar tropical temperatures for this term right here. And then if we do that, we have to change this term. So instead of lambda, we use theta. And this converts the atmospheric temperature to a TOA flux response. This replaces lambda. All right, so now the beauty of this is it gives you a better correlation against top of atmosphere flux. So here's the regression of TOA flux against surface temperature. This looks awful. Here's a regression against atmospheric temperature. It looks better. You can see all the statistics are better. And so atmospheric temperature gives you a better description of top of atmosphere flux. It's a more natural variable. And I can go over the reasons for that if you're interested in that. So theta, so when we ask the question, what is theta? If it's actually better constrained because there's a lot less scatter. Here, we have no idea what lambda is. Lambda could be extremely wide value because of all the scatter in this. But theta is well described. We can look at the PDFs. See how wide this PDF is, extremely wide. Again, because of all the scatter. This is actually reasonably well constrained. It's because top atmosphere flux correlates better with atmospheric temperature. So in this revised framework, we can now make a better estimate of climate sensitivity, as I'll show you in a second. So, so in this framework, this is what the temperature is. This is what the climate sensitivity is. This part right here is exactly the same as the equation I showed you before. It's F over the observed theta. This is what we're measuring. This is the forcing times a term which converts this interannual theta into a long-term force theta. Now this gives us the atmospheric temperature change in response to doubled carbon dioxide. Then we multiply it by another term which converts the change in atmospheric temperature to change in surface temperature. So if you kind of multiply it through, you'll see that this works out and gives you the equilibrium change in surface temperature in response to doubled carbon dioxide. So again, we're going to do exactly the same thing we did before. We know what we have PDFs of all of these terms. This is the forcing for doubled carbon dioxide. We use the same thing we did before. Here's the PDF of theta from series. Here is the PDF of the ratio of theta, internal variability, to 4 times CO2. You can see it has an average value of about 1, which kind of makes sense to me. And then here's the PDF of the surface temperature to atmospheric temperature. We get this from a model also. And if you put all these in, you Monte Carlo it, you come up with the climate sensitivity. This is what it gives you. Now this is actually a lot better constrained. I don't know if you can remember, but the values here, out here at 5 or 6 degrees, are a lot lower. It was sort of, the previous one sort of had this long tail going to high values. This is much better constrained at the high end. Now the other parts that look basically the same. You still get, you get a little bit higher bottom end array. Instead of 2 degrees, it's 2.4 degrees. The high end is 4.5 degrees of the likely range. So it says the IPCC, the high end of the IPCC at 4.5 is about right, but the low end should be a little bit higher. And the median is 3.3 Kelvin, which is very close to what the IPCC said. So again, it's in some sense, it doesn't call for a huge revision of the IPCC's estimate, but it does say those low values we're getting from the 20th century very well may be just initial condition problems. They don't represent the true climate sensitivity of the system. So this is pretty good, but any analysis you do, you have to think, where could you go wrong? All right, so let's think about how this could be wrong, okay? All right, so we can go through term by term and ask, how well do we know these things? All right, so forcing. We know forcing pretty well. It's essentially a radiative transfer with carbon dioxide. If you think we don't know how to do that, we don't know how to do anything. All right. All right. These measures right here, these are measured. So this is series measurements and surface temperature. We know those. Okay. I have extremely high confidence in series data. I have extremely high confidence in reanalysis surface temperature. This term right here, we have some measurements for. And the models look reasonable, and the physics is reasonably well understood. Okay, so atmospheric temperature is just controlled by surface temperature through convection, which ties them together. It's likely the models are getting those right, and we can test them over limited periods of time. You know, we have good atmospheric measurements that go back to the late 70s, so we can test them. The models look like they do a reasonable job in this. So if there's going to be a place where this calculation is going to fail, it's going to be here, because we really don't have any theory for how the response to interannual variabilities should vary compared to the response to carbon dioxide. So these are different. These are the physics is completely different. One of them is this coupled atmosphere-ocean mode, El Nino. The other is this forced warming. And so we don't really have a theory, and we don't have any measurements to check the ratio. We can't compare the ratio to measurements. So that's kind of sad. But on the other hand, there are some things that give us some hope that this is right in the model. So the first thing is we can compare the numerator to observations. So we can get this out of a control run from the model. That's where we get the internal variability, get this out of control run, and we can compare this to the observations. And in general, the models do a pretty good job. And so what that means is, in order for this ratio to be wrong, there has to be some error in the denominator that's not in the numerator. All right, and I've spent a lot of time thinking about this, and I can't think of any way of any error that could be in there. But I thought that's not good enough. Let's actually see if we can do some experiments to test this. So we did an experiment with the MPI model. I should acknowledge Torsten Mjortsen and his graduate student Diego Jimenez for doing these runs. So they took the MPI-ESM 1.2, which is a slightly more advanced version of the model I showed, and they ran 3 different versions of it. So these have 3 different cloud feedbacks. So the standard model is just their standard model. IRIS, people that follow the climate debate, is Dick Lindzen's theory that essentially that there's this negative cloud feedback as the climate warms. And then there's a high ECS version where they change the entrainment of the models to give themselves a high cloud feedback. And if you look at the climate sensitivity, the standard model has 3, the IRIS has 2.6, and the high ECS model has 5.2. So it's quite a different range of climate sensitivities because they have different cloud feedbacks. Now, as you would expect, maybe not as you expect, it turns out that if you look at theta internal variability, they all scale with this. The high climate sensitivity model has a very different theta internal variability than the IRIS model. So the change in cloud feedback is reflected in the theta in response to internal variability. And in addition, you also see a very big change in the response to 4 times CO2. But if you look at the ratio of these two, which is what we care about, the ratio is very close to being is very similar. So what it says is that as you can imagine there's some feedback in the real world that's not in the model. It probably wouldn't matter that much because it's not going to be in the numerator and it's not going to be in the denominator. And what this says is we can change the feedbacks. It doesn't change the ratio that much. So I think this is believable. Again, you'd like to do more work. I have to say, if I was a graduate student, I think there's a lot of work to be done on coming up with a theory for this, a theory for how the response to short-term variability and how the response to long-term force changes. I think that would be a really high-impact paper. So there's still stuff to be done on this. Okay, so I'll just wrap up here. With a few points to remember. The first one is be very skeptical of climate estimates from the 20th century. They're strongly influenced by internal variability. But I guess I think it's a little confusing. You think about this instead as initial conditions, because I use internal and interannual variability in different ways in this talk. So this should be, in your mind, changes to initial conditions. But we can use short-term interannual variability to make an estimate that agrees well with the IPCC range, except has a high or lower end. I think the field is undergoing a revolution in climate sensitivity right now, and I expect the next IPCC report to have a higher bottom end. And as I said before, this is a really good problem. Understanding how the climate system responds to short-term variability, which we have really good measurements for, how that maps onto the response to long-term variability, which we don't have good measures for, is extremely valuable. If we could have a good understanding of that, that would be a real advance for the field. And I'll just wrap up there. I'm happy to answer questions. Thank you. Yeah.
I wanted to ask about the IRIS, actually.
Okay.
I remember that in grad school when it first came out from Dick Lindzen.
Yeah.
It was a Dan's paper, and then I think Dennis Hartman immediately followed it.
Right.
Essentially seems to shoot it down.
Right.
But I'm just curious that there's a version of the model that has the IRIS. I mean, is that really a realistic, that strong a negative feedback?
Okay, so the whole idea, so in 2015, so you're right, so 2000, Lindzen writes his IRIS paper. Essentially, to give you an idea of sort of how open-minded the scientific community is, people really took it seriously at the time. I mean, if you remember that, people analyzed it, they took it very seriously, and Dennis Hartman wrote a paper which in my opinion really did made a very strong argument against it, and so it kind of disappeared after that. I mean, there were a few other comments and replies. It didn't really go anywhere beyond that. But the whole idea of the IRIS, by the way, is that as you warm the climate, you get higher precipitation efficiencies. You get more rain falling out. That makes cloud area smaller. That means you get more infrared to space. And so you end up offsetting the warming. Now, so in 2015, Bjorn Stevens and Torsten Mjortsen wrote a paper in Nature Geoscience or Nature Climate Change, where they essentially forced an IRIS in their model. It was not based on any physics. They forced the model to rain out a lot of precepts. So that kind of forced, and what they found was you get more infrared out, you get more solar in. And those almost canceled. You can see in the table, if you remember the table, it was a difference of about half a degree in ECS. It's about 3 degrees versus 2.6 degrees. And in fact, Andrew Gettleman ran the CSM, one version of CSM, and he got the climate sensitivity to go up when you do that. So it's pretty close to a zero net effect. So in their paper, it wasn't that it was a big effect, because it was not a big effect, but it's a small half a degree effect, and it's not because the model actually generated that because of physics. It's because they forced the model to do that. And I will say it did solve some other problems. The model had a more realistic hydrologic cycle response. So it may be there's something there, but it's not going to do what Linzen argue, which is give you a very low climate sensitivity. There seems to be no evidence that that's the case, even if there is some evidence for his underlying mechanism. Yeah.
So, it's tough to find that your idea that these two parameters are scale are very plausible, and I think there's ideas of scale invariance in physical systems that tend to support that. So one thing that struck me is that you went from surface temperature to atmospheric temperature, and presumably people were looking at surface temperature because, of course, that's where we live.
Right.
Now, if you're going to take the step of going to an atmospheric temperature, well, atmospheric temperature might seem a rather arbitrary choice when you're looking at fundamentally at energetic flows. So if you're going to make a jump, why not go to an energetic quantity for the atmosphere rather than the simple temperature, like, for example, the moist static energy? That would allow for things like latent heat and the gravitational potential, and latent heat being the key one.
Yeah, I haven't thought about that. I mean, the reason we went with atmospheric temperature is a little bit of a post hoc explanation, is that, so for most things, it doesn't matter whether you use surface or atmosphere, because they do correlate pretty well. But for low clouds, the atmospheric temperature is what controls the stability of the atmosphere. That changes more than the surface temperature. And so that actually, so it's the shortwave clouds that the atmospheric temperature does a better job on. Now, otherwise, you can use whatever you want as a variable.
Even there, let's say you were to choose the stability, which would be a great argument. It's a saturated stability that's really controlled rather than just dry stability, in which case the latent heat term would seem to be a suitable addition.
Well, let me just say, I by no means think that the atmospheric temperature is the end of the road on this. I think I think we need to get out of thinking of just surface temperature, because the reason people use surface temperature is it does correlate well on these runs that have huge amounts of forcing in them. But if the run doesn't have a lot of forcing, then surface temperature kind of breaks down. So I think there probably are better ideas. I mean, I'd like to talk. Let's talk more about that. About other variables. So I think there probably are other things we could change that would make more sense. Other questions, comments? Yeah.
At the very beginning, so you have a slide showing the year 2000, you have big jump. So I just wonder, that's 2000 per year or year 2000, or what's the big difference?
Oh, that's just the year 2000 of a run. I'm not saying that actually happened.
Okay, so why that year is special? Because
it's just they ran it. There's nothing special about the year. So let me put it. That's probably the better plot.
Yes, because you see this.
Yeah, there's nothing special about the year. They just ran it for 2,000 years to do a control run, and then they said in 2000 we're jacking it up to 4 times CO2. We're not. This is not designed. This is designed just as an energy balance primer to explain how energy balance works. It's not designed to be realistic.
So it is not the model results. It is a scenario. So just
No, this is a model, but it's an abrupt 4 times CO2 scenario. So it's not at all realistic. It's just people do these abrupt model runs because it allows you to separate forcing from response. If you're adding CO2 and the climate's warming, you've got forcing and response going at the same time, and you've got to separate those. If you jack up the CO2 and then hold it fixed, then you watch the climate evolve. Everything is the TOA flux is all the response. It has no forcing mixed in with it. So the reason people do these abrupt 4 times CO2 responses is, so what I can do is I can tell you that this change is all due to the warming climate, because there's no change in forcing over this. If I was doing like a 1% run, then part of the change would be due to adding CO2, and part would be due to the warming climate. So it's just a conceptual, if you look at the CMIP literature, people love these 4 times CO2 runs. They just love them, because they're easy to analyze. Yeah.
So what is the practical importance of knowing the climate sensitivity, given that there's so much contribution from internal variability, which overrides it? It can go in any direction.
Yeah, okay, so that's a really interesting question. So the short answer to that is internal variability is important as long as you don't have a lot of warming. So we've had about 8, maybe we've had 1 degree C of warming over the last 100 years. Internal variability is kind of comparable to that, maybe half as big. If we have 8 degrees of warming, internal variability is still only going to be half a degree. And the difference between a climate sensitivity of 2 and a climate sensitivity of 4 is whether you have 4 degrees or 8 degrees. So as you go out and you get more forced warming, the contribution of internal variability becomes smaller and smaller and smaller. The reason that we're having trouble with it is we haven't had a lot of warming yet. I mean, that's the scariest thing. You know, we're just at the very beginning, and we're seeing these what look like big changes. Yeah.
So you mentioned that the IPCC report may shrink the uncertainty, but what do you sort of see as the ultimate in terms of how much reduction in uncertainty can you really get? So,
well, you know, there is one number. You know, there is, if you had 1,000 Earths and you double carbon dioxide and you let them run for 100,000 years, you know, there'd be one number for that. So there is a number out there. How close can we get to it? I don't know. And I'm not sure, you know, getting back to what Thomas said, I actually don't know that it matters that much. I mean, the policy response to all of these things is the same, essentially. You want to cut emissions as fast as you can. It doesn't really, I mean, if it's 2 degrees or 4 degrees, it's like, are you going to get run over by 1 locomotive or 2? You know, in both cases, you get off the tracks. You know, it doesn't actually matter. It doesn't really matter. So, you know, I think, you know, from a policy standpoint, it may not actually matter that much. Yeah.
Does it, so you're saying it doesn't matter, but surely the speed at which we emit CO2 will then lead to a quicker warming or a slower warming, so we can emit quicker.
Yeah, let me be clear. When I said it doesn't matter, I meant it probably doesn't matter for what your policy response is. I think it does a lot matter on how much suffering, how much you're going to suffer. But as far as what we do as a society, it doesn't matter. But, you know, if it's 4, you know, people your age, you know, you are going to have a much tougher life than if it's 2. I mean, it's going to be a lot worse.
I think what you're saying, as long as we do something, if we do nothing, that's something different.
Yeah, well, I mean, I would say more than something. I mean, what we want to do is we want to cut emissions as fast as we can, even if it's 1.5 degrees. That's what you want to do.
Okay. Well, maybe thank our speaker for an excellent talk.